Oh, thank you very much. Okay, so certainly, thank you. Okay, so let's continue. Again, I need to tell you this is just an introduction. Okay, so for the service tension force, you don't need to know too much, but just know some phenomenon related to service tension force. That's enough for you. But sometimes I would like to talk more about this because I think it's interesting. So anyhow, the details. And also, if you just can recall what you have learned in theoretical mechanics, and I think you still can figure out what happened here. Just like this is the equilibrium equation in vertical direction. Okay, so this is the pressure difference between the inside and outside the water. Okay, so this is a acting area, the projection area. Okay, the projection area because the projection area in vertical direction. Okay, so anyhow, if you just forgot what you have learned before, it doesn't matter. You just only need to know that for the same fluid, same tube, and I mean, same fluid, same material, tube material, and the height is water level, the height of the water, the column will decrease with the increase of the tube radius. Okay. You know, sometimes constant value, yes, sigma has a constant value if you got the same fluid and same tube. Here we just have say this. The sigma surface tension actually decided by the material. Okay, the contact angle decided by the solid and fluid, and sigma if for the same fluid with and the same gas, just the interface. We mean the density for the two just liquids or gas is the same, so the sigma will be a constant. Okay, so it depends on the here for the liquid. Okay, so yes, same liquid, the sigma will be the same. Okay, and theta, the contact angle, will decide by the liquid by the solid both. Okay, and gamma is the specific fate of the liquid. Okay, R is the tube radius. Okay, so in real life, if it's water, we will say this: the water rise above the water outside the tube. However, if it's um, just like here, this one, I just forgot. Sorry. Um, Let me just remember what's, for example, if it's non-wetting, if it's non-wetting, so the level will just will be compressed. And so you see here, for example, just like um, uh, this non-wetting liquid, and the instead of to rise above the outside level, and it's compressed. Okay, it's non-wetting, and you can just you say for this is wetting. So because it's wetting, so the water will be put to the liquid, and that's why it will rise. But for this one, because the molecule, the liquid molecule, have stronger forces compared to the solid molecules, so the molecules will attempt to shrink themselves, well, to push the solid boundary away. So that's why it is compressed. Okay. So this is all about the surface tension force. And for the surface tension force, because for you, for civil engineering students, you should know that, just in some places, just like if you go to forest, or if you live in the first floor, you will see sometimes the wall will become wet. It's due to what? The water become wet. Or if you go to the forest, you just go to the hotel, and it's better for you to choose a room in the second or the third floor instead of the ground. Why? Because of the surface tension force. The water will just go up, and so the wall, the room wall will become wet. That is the surface tension force. That's because of surface tension force. One more thing about surface tension force, just like the tree, right? And the flower. The tree is high enough, but because of the surface tension force, and so no matter how high it is, you still got enough water supply because of the surface tension force, because the capillary effects. Okay, capillary effect is due to surface tension force, and due to the capillary effect, the ground is wetty, is humid, and the wall is sometimes you say here in China, in Guangzhou province, is quite humid. In spring, and because it's rainy and windy, the wall sometimes can drop water. Okay, yeah, because the capillary effect. Okay. And then the vapor pressure of liquids. We talk about vapor pressure of liquids because sometimes later on, and some students will study the cavitation. Okay, so what's vapor pressure? First, evaporation takes place because some liquids molecules at the surface have sufficient momentum to overcome the intermolecular cohesive forces and escape into the atmosphere. This one, we all know that this because the molecular force by the gas is much not when it's larger than the intermolecular forces, and so the liquid molecule also will go to the air. This is evaporation, and evaporation when the what can cause evaporation. We know that when in normal temperature, the intermolecular cohesive forces of the water will be much larger than the gas molecular force, right? However, the molecular force by the water will decrease with the temperature increase, right? We have learned last week, right? When the temperature increase, the molecular distance between fluids, between water, will increase. And so their intermolecular cohesive forces of the waters will decrease. And it happens to some point, just like to 100 Celsius, the gas molecular force is larger than the molecular force by the water. And so some water molecules will go to the air, and that's called evaporation. Okay, when an equilibrium condition is reached, what means equilibrium condition? That means some gas molecules go into the water, some water molecules go to the air. So if the molecular numbers are equal, we call it equilibrium condition. when an equilibrium condition is reached, so that the number of molecules leaving the surface is equal to the number entering, the vapor is said to be saturated, and the pressure of the vapor exerts on the liquid surface is termed vapor pressure. So vapor pressure is at what condition? When the equilibrium condition is reached. What means equilibrium condition? Means how many in, how many out, how many molecules leave, how many molecules enter, and that's and at that time the pressure by the vapor is called the vapor pressure. Okay. Because the development of a vapor pressure is closely associated with molecular activity, the value of vapor pressure for a particular liquid depends on temperature. Yes, because we know that molecular activity uh, is greatly related to temperature, right? And so boiling, what happens to what is called boiling? Boiling vapor pressure equals the ambient pressure, and then this is there will be boiling. We know that heat the water and the boiling will happen, right? And for Chinese, we always drink boiled water. Okay, I don't prefer non boiled water. Okay, so at a given pressure, boiling is induced by raising the temperature because we know within the temperature, the water molecule forces will drop. And that's why the water molecules can go to the air. Okay, so that separation can happen. Okay, at a given temperature, boiling is induced by knowing the pressure. Okay, that's why we always say if you go to um, NASA, which is much higher altitude than Chengdu, and you can only use um, high pressure utensils to cook. So unless and the rice will be not cannot eat. Okay, so this is the vapor pressure. If the fluid pressure is lower to the vapor pressure, and boiling will occur, and just for example, and it may occur in flow through the irregular narrow passage of a valve or pump. When vapor bubbles, we know when it is boiling, there will be bubbles, right? When vapor bubbles are formed in a flowing fluid, they are swept along into regions of higher pressure, and you know because outside the pressure is higher, and then they will collapse, right? Because there is a bubble outside, the pressure is larger, inside the pressure is lower, so the bubble definitely will collapse, and the collapse has sufficient intensity, and it will cause structural damage. Actually, you will see in factory the valves, most of valves actually are damaged because the cavitation. The cavitation is because the formation and subsequent collapse of vapor bubbles in a flowing fluid is called cavitation. It's the bubble collapse will have very huge structural damage. Okay, this is a vapor pressure. It's just a brief introduction, and later on, if you do research in this area, you can learn more. Okay, and the force acting on a fluid body. What is a force acting on fluid body? We have learned this before in thermal mechanics. We know force can be divided into two parts. One is body force. What is body force? Body forces are distributed over the volume of a fluid. They arise from action at a distance. That means body force is non-contact force. and they will result when a fluid is placed in a gravitational magnitude electrostatic or electromagnetic force field. So for us, body force, now what we have learned, have used often and often is gravitational force, right? Gravitational force is body force, is non-contact force. And so gravitational body force per unit mass is the gravitational acceleration. And then surface force. Surface forces act on the boundary of a fluid body by the surroundings through direct contact. So it's very important. Surface forces are contact forces. Okay. Fluids only apply a surface force to their surroundings. So pressure force, definitely they are surface force. What we have learned surface force before, just like this is the ground and this is the box. So the supporting force is surface force, and the friction force is also surface force. Surface forces are contact forces. That's what we have done before in thermometric mechanics. In thermometric mechanics, we say there is a ball. There is a ball and it will downwards, and at some point it will fly, right? And when we would like to know the velocity when it starts to leave the slope, and we know that because you already studied thermometric mechanics, we know that it means at the when it leaves the slope means the normal force, the contact force should equal to zero. Why? Because contact force, surface supporting force should be a contact force. Okay. So surface force we always use the force per unit area, just like pressure. Okay, a surface force, just like here, can be normal force perpendicular to surface and tangential force acting parallel to the surface. What does that mean? Just like here, we got the force and we just decompose it into two components. One is perpendicular, the other is parallel to the surface. Just like when we study this is a solid surface, and then we know that there is a box, and we know that the actually the supporting force is not perpendicular to the solid surface. So we can decompose it into two. One is perpendicular, this is normal force. One is parallel to the surface. This is a friction force, right? So this is same. Sure, this is two-dimensional. If it's three-dimensional, this force can compose to two more components. Okay, so this is for the surface. We use the subscript n to indicate the normal components of the surface force F. We use subscript T to indicate the tangential or the shear components of the surface force F. This is what we know about fluid, the introduction part, okay? So let's continue our study. So body force, surface force, body force, gravitational force, surface force, pressure force are very good examples, okay? And sure, definitely sometimes you have other body force just like magnetic force, okay? But here we don't consider that. We'll continue study about the fluid statics. So for the introduction part, we don't have assignments, but for the fluid statics, we will have assignments, okay? And also after we finish the study of fluid statics, we will have the first quiz, okay? So let's see. Okay, let's start fluid statics. I should share to you. Sorry. Okay, just like what we have learned in thermal mechanics, fluid mechanics also will study fluid at rest, that's fluid statics, and also we will study fluid in motion, that's fluid dynamics. And for fluids at rest, we still have a lot of applications. Okay, so we know that fluids cannot remain at rest under the presence of shear stress. This is the definition of the fluid, right? No matter how small the shear stress is, the fluid will keep continuously deformation, right? So that's definition for the fluids. That means fluids, if there is shear stress, the fluids will deform. So in other words, fluids at rest cannot support any shear stress. That means they are free of shear. So for static fluids, and we only need to talk about pressure force. We only need to talk about the normal force, okay? We sometimes we need to determine the pressure distribution within a static fluid, and this is the main task for this chapter. And we have another application with fluid statics. Just for example, pressure distribution is still atmosphere and oceans. Pressure measurements using manometers, forces acting on submerged solid bodies, buoyancy and stability of floating bodies. Okay. Here we need to address one thing: fluid stick, a static fluid at rest. Here we mean there is no relative motion between the solid boundary. So fluids in rigid body motion are also free of shear forces, and their analysis is still quite similar to fluid statics force. Okay, we already talked about the surface tension or surface force, body force, surface force, contact force, and sometimes we use surface force per unit area. So we call the stress or the pressure. Body force is no contact force. It's we use body force per unit mass, just like acceleration. Okay. Here we use capital X, Y, Z to indicate the X, Y, Z component of the body force. Okay. For pressure at a point, we know it will be when the area all goes to zero, because pressure is actually surface force. So here, when the area goes to zero, the limitation of the delta F over delta A will be the pressure, or the normal force per unit area at a given point acting on a given plane is the pressure at a point. And its unit can be par or Newton per meter square in the international unit system, and can be also use ATM, mmHg, okay, the kg per centimeter square. And we sometimes, if in the British unit system, it will be pound per square inch, okay. For hydrostatic pressure, we have two very, very important properties. First, the pressure is always vertical to the surface and point into it. The second is at any point, pressure is independent of orientation. Why I can do a very simple verification. First, hydrostatic pressure is always vertical to the surface and point into it. You see, we have here Mn assumed interface, and then assumed interface in the fluid, and there is a point K, and according to we can just draw the pressure force. If the pressure force is dp is not perpendicular to the surface, and so definitely it will have two components. One is normal to the surface, the other is tangential to the surface, right? If tangential to the surface, if here is not equal to zero, what will happen? The fluid cannot resist the shear stress, right? We cannot resist the shear force. This one is tangential to the free surface. So under this action of the free surface, according to the definition of the fluid will start to flow, right? It can't remain static. So it's impossible, right? This must equal to zero. Or the pressure, hydrostatic pressure, can only be perpendicular to the surface. Okay, and pointed. It's very important. Okay, we just so the hydrostatic pressure in the equilibrium liquid can only be perpendicular to the pressure surface. And then the second one, at any point in a static fluid, pressure is independent of overtension. Again, we just draw FBD and do force analysis, okay? And this is a fluid. This is a fluid in two-dimensional, we take this triangular fluid element, and then we draw FBD. This will be the weight, right? This will be the weight of the fluid. G equal to no G. Though is the density, G is the acceleration, gravitational activation, and this one will be its volume, right? This one will be its volume. B is actually the width of the element, and we just can take it as one. So this will be the weight of this fluid element. And now also except this body force, except this gravitation force, we also have the pressure force. Okay, we have pressure force. Just now we know the pressure force always perpendicular to the interface, right? And px, pz, because this is x, this is z coordinates, this is p normal, okay, because p normal perpendicular to the slope. And so the forces on left and upper surface will be pressure force equal to pressure times the area. Delta y, delta y is actually b, okay. And so the normal force, the normal pressure force on this one will be the pressure force times area. The area here, the length will be equal to delta z divided by sine theta. And so according to Newton's second law, because the fluid is at static, that means the fluid is in equilibrium. So we can write down the equilibrium equation in x direction and in z direction. Okay, in x direction, we have this px times its area, it's a pressure force to the right, and this will be this normal force, the times sine theta will be its x component. So we will have px equal to pn. In this direction, we can also write down the equilibrium equation. We have found that pz equal to pn plus the weight of the fluid. Because we here this point in static fluid, so that means delta z goes to zero. It's fluid particle actually locate this space point, and delta z goes to zero, and so this one the fluid weight goes to zero. So finally, we have Px equal to Pz equal to Pn equal to P. What does it mean? It means the pressure at a point in a fluid at rest or more is independent of direction as unknown as there are no shearing stresses present. This is known as Pascal law. Okay, so the pressure at a point if the fluid is in equilibrium, the pressure force will be always independent of the direction. Okay. Sure, if it's in moving fluids, that means if there is shear stress, it will be not this case. Okay. For this part, we should always remind ourselves pressure is the only service force. There is no shear force. There is no shear stress. And pressure distribution relates to body force only. It will apply to dams, buoyancy related instrument, okay, for the power system, connected vessels. As we dive deep into the sea, we will feel more pressure in our ears. Why? Why as we dive deep into the sea, we'll feel more pressure in our ears? If we stand just here on the ground, the pressure in our on our ear will be the atmospheric pressure. But if you dive deep into the sea, the pressure on your ear will be the atmospheric pressure plus the weight by the sea water, right? So when we try to high absolute atmospheric pressure decrease, okay. Yeah, water pressure, right? Following fluid element in a static fluid is not moving because no net force acts on it, right? Because according to what we have learned in thermometric mechanics, for fluid at rest, for static fluid, that means the fluid is in equilibrium. So there will be no net force because according to Newton's second law, net force will result in acceleration, that's for sure. So just for example, for here, if we got the fluid element and then we just draw FBD, so this fluid element definitely there will be body force, but that means the fluid weight and or the gravitational force, but because it's in static, that's for sure it should be balanced by another force. This force is actually the pressure force. Okay, this force is due to the difference in pressure acting on different phases of the fluid element. Okay, so this is what we will learn on Thursday. So fluid at rest. Okay, for this part, you need to know that fluid at rest. That means there is no shear stress. Okay, we only here include body force, the gravitation force, and pressure force. One more thing for fluid rest, we mean there is no shear stress. So there is no relative motion. Okay, just like if you rotate a cup, actually the water also rotate with the cup together, but there is no relative motion between the water and the cup. So we still regard them as fluid and static. Okay, because there is still no shear stress. Okay, and so also very important thing is we need to know that for fluid at rest, the pressure is always perpendicular to the surface. And the pressure is equal to, is independent of its rotation. What that mean? Just for example here, let's say you here. It's very important. I think some students let's see, and we will talk about later. Okay. You see, just for this, the pressure will be always perpendicular to the surface, okay? The pressure will be always perpendicular to the surface. This is the surface. This is the surface, and this is surface. The pressure will be always perpendicular to the surface. And here at B, you see the pressure from AB, the pressure will be perpendicular to the surface, or perpendicular to AB and point to AB. And BC, pressure will be perpendicular to BC and point to BC. And it's very important. Pressure is independent of its orientation if fluid is at rest. That means here, this one is gamma H1, this one is also gamma H1. They are equal to each other, okay? And for here, you see, for AB is a curved. AB is curved, and again, if fluid is at rest, the pressure is always perpendicular to its surface. We know this one will be known as centers, okay? And so here, all the pressure should always perpendicular to surface. So this one, this pressure force will intersect at point O. Okay, we will explain this more later on Thursday. Okay, see you Thursday. That's all for today. See you Thursday. If you have